Hello, so today we are going to talk about this problem called reduce array size to half. So let's see what the problem says. So the problem says we get an array and we want to choose a set of integers and remove all the occurrences of these integers in the array. So we want to choose some integers, a set of them, and we want to remove all of the occurrences of these integers in the array. And the goal is to return the minimum size possible so that we remove at least half of the integers in the array, right? So what's the minimum size of a set of integers that we can remove from the array so that when we remove them from the array, at least half of the integers would have been removed in the array. Let's take a look at an example to make sure we understand. So let's say this example, we have this array. So the array size here is 10, right? So length of array is 10. And if we take a look, we can remove 3 and 5, and this would mean we will remove all occurrences of 3 and all occurrences of 5. So let's strike this out. So we remove this, we'll be left with only 3. How many we removed? We removed 4, 3. So we removed 7 integers, right? And the goal here is so that we remove at least half of the integers in the array, right? And so with this, we removed 7. And half of the array is 5, 10 divided by 2, right? And so we removed more than half, right? Which is what's required, at least half, either half or more. And so that means that the minimum size possible is 2, right? Because it's 2 numbers here. Because if we try to remove any, like just one number, we can try with 3, but then we would have removed only 4, which is smaller than 5. If we try to remove 5, then we would have removed only 3, still smaller. Similar thing for 2 and 7, right? So the minimum is 2 actually. So we can output 2. The second example is we have this array, right? 1000 2 times and 3 7. So we can just remove 1000, right? This is just one element, and we would have removed 2. 2 integers would be removed, and so the array size is 4, so half of it is 2. So we remove it at least half, we remove 2, right? So all we need to remove is just one element, and so we output 1, right? So this is the problem. Now let's see how we can solve. Okay, so let's see how we can solve this problem here. So with the first example, the array that we had so the array had 4 3s, right? And then 3 5s. And then 2 2s, and then 1 7, right? So the length here is 10, and so half size is actually 5 here, right? So you can see what we did in the example there. We removed 3s, and then we removed 5s. And that left us with 7 removed, which is bigger or equal to 5, right? And so you can notice one pattern we did here is that we removed the integer that occurred the most, right? So this is just one thing we can notice. So observation. Removing integers that occurs the most often is occurrence. So this may be a good greedy strategy, right? But with greedy, we need to always make sure what we are doing is actually working, right? So greedy usually gets proved with kind of a formal argument with either 2 types of proofs. One of them is exchange argument. The other one is the other ones is stay ahead. You can read about this, but I'm just going to kind of give you like the idea of the proof, but not do it explicitly. And the thing here is exchange argument, right? So if we don't go by this hypothesis, if we don't take the integer that occurs the most, then we will take, let's say for example, 2, right? In that solution. In a solution where we don't take the greedy choice, we will take one that occurs less. We can always replace that number with the one that occurs the most. And in that case, what would happen? the size of the removed elements will go down, will go up, right? Size of so let me just write this down. So if we pick, let's say we pick a number with lesser occurrences, right, in the optimal solution, then what this would mean is that we can replace that with the greedy choice. Right? Let's say this occurrence here is called occurrence O, and this here is called occurrence G from the greedy solution, right? So we know that greedy is bigger, always takes the highest number of occurrence, is bigger than the highest number of occurrence of O, right? And so what this would mean is that the size of the greedy solution, the size of removed element in the greedy solution, is bigger than the size of the removed in the optimal solution, right? Because we remove all the occurrences of the number, so we'll remove occurrence of G, right, instead of occurrence of O. And so since this is bigger, the number of elements removed is bigger, right? So what this would mean is that basically greedy removes more than the optimal solution, moves more than optimal solution. Well, what this would mean is that, well, we could just use greedy, right? Because it's optimal, since the size is bigger than the optimal, and we know that the optimal is bigger or equal than the length of the array divided by 2. So what this would mean is the greedy solution is always valid. So we could just use that, right? So this is kind of less formal proof of it, but you could try and do more formal one. But this is the main idea, is that picking the greedy choice over whatever optimal solution we had won't make the solution worse, right? It will always be either better or at least as good, right? Because here the size of the ones removed would be at least as we could even like say, okay, what if the greedy choice just picks one that has the same number of occurrences even, right? And so we'll still be as good, right, as the optimal solution. And so this is the main idea. And so the main idea here is to do a greedy algorithm, right? So greedy solution. And the greedy approach here that we will be doing is that each time pick the number, the integer occurring the most that is left in the array, right? That hasn't been removed yet, right? That hasn't been removed yet. And so this is the approach we'll be taking. Now, how can we kind of do this, right? So with Python, it's easier, right? We can just have the occurrences. So we can have a counter, right? With Python, you have the collections. In collections, we have counter, so we can just count the occurrences of the elements in the array. Let's say we have this example with 4 3s, 3 5s, and 2s and 7. What we can do is we can kind of have a counter. So we'd say 3, we have 4 occurrences, 5, we have 3 occurrences, 2, we have 2 occurrences, and 7, we have 1 occurrence, right? And so we'll just pick the most common ones, right? And so and then we will keep going down. So we'll start from the most occurring ones, right? So in count, we can either sort like the values, sort by the values here, the number of occurrence, or in counter we have this function called most common that just gives us actually that exact same thing. It gives us the elements sorted by the occurrences. And so what do we need? We need to find the minimum set, the minimum size that will give us at least half the size. That's what we are looking for. So what this would mean is just iterate over the most common elements. most common in counter, right? Of course, if we are using Java or any other language, we can use a map and just do a first pass where we count the number of elements and just kind of simulate having this counter. And this most common, and then after that we can just sort by the value. So we can also do that in languages that don't have this counter. So we iterate over the most common encounter and keep adding occurrence. So this would be occurrence and this is value, and keep adding occurrence value, and then stop as when total occurrence, right? The total number, so we will be adding to total number of occurrence is bigger or equal than half the length of the array, right? Because that's what we are looking for. And basically we don't even need to like physically remove the elements from the array, right? Because we'll just consider, okay, we removed 3, so let's just add the count of 4. And we removed 5, so let's just add all the occurrences of 5, which are 3, right? And so that way we can kind of simulate it. Okay, so we have the greedy approach. We know what strategy we are doing, and we know how we can accomplish it, right? So let's just write the algorithm here. Okay, so our function would be, let's call it minimum size integers or something like that, and we get an array as input. Okay, and so the first thing we need to do is have something that have the counter and have something that holds the total number of occurrences. So just initialization step. Okay, so let's do that. So the first step would be total occurrence, which would be equal to 0. The second step would be the counter, and let's just call these occurrences, and so it's counter array. So we will need to import that counter function, of course, so that would be just from collections we can import counter. And then what we are interested in is only the most commons, right? So that we can get them in sorted order. Most commons will return all of them, but in sorted order of occurrences. And so that's what we are interested in. So let's just add that here. So that we get it in sorted order. And then the next step would be to loop through this occurrence here, so that we can, so just doing this step, iterating and keep adding until we reach this stopping condition. And so to do that, we'll just do a for loop. And then so this is the number. We are not going to use the value itself, so let's just put underscore here for it. And then we will get the occurrence. And this is in occurrences. And then after that, we need to take, so we need to add to the total occurrence. So to do that, we can do total occurrence plus occurrence. And the other thing we need is, we need to identify, sorry, this is the total occurrence. We need to identify what we are interested in, what the function wants us to return is the size of the set. So for example, here we know that we need to remove all of these, right? All 3s and 5s. So what we want is actually the size of the set of just 3 and 5. So we need a counter to keep track of these, right? And so let's have a count here that is equal to 0 initially. And now here, once we, and so now here, we need to increment the count by 1 because we just added one occurrences of one of the integers. And so let's add that, so +1 here. Then after that, we need to check our stopping condition. So if the total occurrences is bigger or equal, so at least half of the array, if that's the case, then we are done, right? We removed the minimum possible number of elements to get at least half of the array size of the array removed, and so we can just return count here, right? Because the count is what counts the individual numbers that we removed all the occurrences for. And so we need to return that count value. Okay. Then the last step is just, if we don't do anything, if we exit the array and we haven't reached this, we can just return either count. So this value would be either we had to remove the entire array, right? And so we had to remove all the elements, and so we can just return that. Yeah, so that's pretty much it. Very simple. We just get the counter, which just gets us the pairs of the value and the occurrences sorted by occurrences. And we loop through them, and we keep track of the total occurrences, which is just like how many integers in the array we removed so far, and the count, which just keeps track of the individual integers that we removed, so the set. And then if we reached half of the size of the array removed, then we return the count, which is the set size. And yeah, so that's pretty much it. In terms of time complexity, you can see we are doing here a loop, right? And then we are doing this construction as well. So, and most common does sorting, right, in the order of occurrences. So we are doing time complexity of n log n, at least. And then in terms of space, we are also having these occurrences that contains the number of elements we have. So O of n as well in terms of space complexity. Yeah, so that's it pretty much for the solution, for this egregious solution. Now let's take a look at the code and run it on some examples. Okay, so let's see the solution here on some examples. So similar solution to what we had in the overview. Yeah, just count and total occurrence. So these are the two variables that we have, and then occurrences to hold the occurrences of the array elements in sorted order of occurrences. And then we go through them, and then we add the occurrence, and then we add the count for each new integer. And if we reach at least half of the array size, we just return. So pretty simple. And then here we have some examples. So this one that we used in the overview, we should remove this. So 2 elements. Here we should remove just these 2, so 1 element. Here we can remove just either 1 or 11, so 1 element again. Here a similar thing, we can remove 1s, and so just 1 element. Here we can remove 1 and 2 to get at least half of the size, so 2 elements, right? So let's run these to get and make sure we get all tests passed, and we do, right? Yeah, so that's pretty much it for this problem. Using greedy, we can solve it pretty easily. Thanks for watching, and see you on the next one.